Hello, I'm Georgiana Esquivias, and today I will be presenting the method for developing a building exposure database for Tanzania. We will go step by step through a series of flowcharts that assist in organizing and determining the type of data that is required for a Level 3 building exposure. A Level 3 building exposure improves upon country-level data by identifying subnational variations in construction patterns based on climate or cultural region-specific norms. As well, a Level 3 building exposure identifies major urban areas and enhances building count or structural mapping schemes. To develop the building exposure, the METEOR team utilized various sources of Earth observation imagery, national statistics, reports, and journals. Additional source references are found in the individual flowchart sections. The building exposure process is broken down into 7 flowcharts. Each flowchart asks a series of questions that helps identify the data and processing step required for determining the population, structural distribution, number of buildings, if disometric mapping is possible, replacement cost, building height, and building area. Here is a modified population flowchart that traces the data processing steps taken for Tanzania. For Tanzania, the population spatial units were obtained by administrative units. There were 3 sources of population data provided by the Tanzanian government partners: an Excel spreadsheet and GIS dataset tracking population at the ward level, along with a separate national statistics report that contained the person per household data, which was important in estimating total number of buildings and building area. Additionally, the Integrated Public Use Microdata Series, IPUMS, microcensus data contains a population estimate. However, IPUMS was used solely for determining building characteristics in Tanzania. As we follow along the flowchart, it illustrates the merging of the GIS data with the tabulated population data. The population data was spread from the ward level to a 3-arc-second grid, which is approximately 100 meters, using disometric mapping. In the spreading process, several Earth observation datasets are used, including global population datasets, which was ultimately used to estimate number of buildings. The population data is from 2012, and there was no scaling to adjust for population growth. The distribution of buildings by structure type typically receives the most concerted attention in a risk study, and this project was no exception. The sources used to develop the exposure include in-field surveys, microcensus data, and expert opinion. There were 2 methods for developing the structural distribution. The first used the IPUMS district census data to develop the mapping schemes using a combination of building roof, wall, and floor material types. Each combination was mapped to a GEM construction type, and the number of households were used to develop a structural distribution by ward. The mapping schemes were developed at the individual ward level. In areas where IPUMS district information was not provided, the neighboring district was used as a proxy. The IPUMS floor, wall, and roof combinations were mapped to pager and GEM classes by ImageCAD staff and reviewed by the Tanzanian measurement engineer Frank Mushi. The second method includes an in-field building data survey collected by the Humanitarian OpenStreetMap team, or HOT-OSM, which was used to establish the mapping scheme for each development pattern. The process was conducted in the urban areas of Dar es Salaam as well as in the neighboring Pwani region. HOT-OSM used a stratified sampling method and Bayesian updating approach. Approximately 400 building locations were surveyed in each of the development pattern types, totaling 2,900 buildings. The sites were surveyed using the hot OSM tools by local staff trained in GIS techniques. Engineers were not present in the initial in-field data collection. However, a second team of fourth-year students majoring in building economics trained by Frank Mushi were present. This team served as validators of the data, whose main aim was to verify the tagging of building in priority areas. Photographs of each structure accompanied each building assessment. The HotOSM building survey data was verified by ImageCAD engineer Mike Gucci and the HotOSM mapping supervisor Emmanuel Combe. All of the mapping schemes were then mapped to a pager standard structural type and overlaid with the development patterns shown in the next slide to create a refined mapping scheme. Based on the review by HotOSM and ImageCAD, it was determined that the iPumps data captured the diversity of the construction practices throughout the country, and the HotOSM in-field survey data captured the diversity of highly urbanized areas. Thus, the iPumps mapping schemes were applied to development pattern 1, and the HotOSM mapping schemes were applied to all other development patterns. The exception being Zanzibar, where due to the unique history of the region and the homogeneous construction type, the iPumps mapping schemes were used for the entire island. Here we see the final results of the mapping schemes, mapped by administrative districts for all of Tanzania. Note, the gray districts did not have counts in the iPumps database, and so the nearest neighbor were used as a proxy. In Tanzania, the accuracy of the number of buildings was aided by several factors, which include the OpenStreetMap building footprint database and the ward-level person per household dataset. The number of buildings per structure class per 3 arcsecond grid cell was inferred using a combination of census data, development pattern sampling, building count samples, and aggregated OpenStreetMap building counts. Population was converted to estimated number of households and disaggregated to the district level from the ward level using the data provided by the Tanzanian Prime Minister's office. Ultimately, the number assumed at the district level will equal the estimated number of buildings established by the census. However, many data sources are used to estimate the number of buildings at any given cell. For each development pattern, a project analyst reviews 3 arcsecond grids selected using a random number generator and identifies cells where at least 90% of the buildings were represented in the OpenStreetMap database. The selected grids were used to train a regression model using a 3 arcsecond Sentinel-1 Global Human Settlement Layer, or GHSL S1. In addition, WorldPop and the high-resolution settlement layer from the Facebook Connectivities Lab and CSIN, and the Global Urban Footprint, or GUF, from DLR were used to spread the remaining number of buildings, or used in places where it appeared to be a better indicator than the GHSL S1. Sentinel-1 GHSL proved more effective in highly developed regions, whereas the GUF was more effective in rural areas. The model was constrained using an aggregated 3 arcsecond OpenStreetMap building count grid as a minimum cell value. As mentioned, the people per household were obtained from the ward level data. Disometric mapping was used to spread the number of buildings from the census administrative units to the 3 arcsecond grid cell. by way of statistical assessment of the moderate resolution Earth observation data to collect Earth observation indicators of settlements and density of buildings. Various remote sensing datasets were used. The following remotely sensed data products were used for the disometric mapping. The data was obtained from the U.S. National Oceanic and Atmospheric Agency, NOAA, NASA, the U.S. Oak Ridge National Laboratory, the European Commission Joint Research Center, the German Aerospace Center, WorldPop, and OpenStreetMap. These remotely sensed Earth observation products and building footprint aggregates establish the distribution statistics for dispersing buildings by urban density and development pattern type. Each of the Earth observation products individually and in combination act as a weight to disperse the known population per Tanzanian district by structural type and determine development patterns to the 3 arcsecond grid cell. To prevent unpopulated areas from being considered as settlements, a mask was created using the minimum threshold value determined by visual inspection in Google Earth and with various specific Earth observation datasets, including Sentinel-1, Global Urban Footprint, VEERS, Landscan, and the high-resolution settlement layer. These minimum values correspond to even the sparsest of human presence. This mask was used to subset the high-resolution Sentinel-1 SAR mosaic, which goes into the machine learning process that comes up with the development patterns. The Global Urban Footprint, the Sentinel-1 based GHSL, and the CSIN Facebook high-resolution settlement layer were not subset because these were good indicators for locating rural settlements. To characterize building density in more populated areas, analysts digitized development pattern training polygons in the top 10 most populated cities in the country. For these cities, the digitized vector data was used directly rather than the classified development pattern grid. The delineations are digitized using Google Earth area tools and saved as KMLs. The base map vintage and source vary by region and zoom level. However, the most current high-resolution satellite images are used. The training polygons and the moderate resolution Earth observation products described above are used in a machine learning process for assigning the development patterns throughout the country, which informs the estimated building density. The intensity of urbanity corresponds to both the building density and the structural distribution. For Tanzania, the ImageCAD engineer characterized 6 development pattern types. Replacement cost values for Tanzania are based on estimates from a study conducted by ImageCAD for several African nations, which more accurately characterizes the per unit building area replacement cost, particularly in rural Africa. Replacement cost was determined by profiling structural durability by development pattern, as determined via remote sensing segmentation and digitization. Structural durability was classified into 3 tiers: temporary, semi-permanent, and permanent. The replacement costs for temporary and semi-permanent structures were obtained primarily from the Resettlement Action Plan, and the replacement cost for permanent structures were taken from structural cost manuals. The replacement cost for each development pattern was determined by applying a weight by mapping scheme for each structural type. This work was done under a separate grant for the Global Facility for Disaster Reduction and Recovery, and applied to Tanzania. Additionally, here is a list of the sources used for determining the replacement cost. A ratio was calculated between the durability classes and expressed as a percentage of engineered construction. For example, semi-permanent construction for a given country may represent 40% of the total permanent construction cost, and temporary construction may represent 20% of the total permanent construction cost. A ratio approach is mathematically equivalent to taking the average value of durability class, but has the added advantage of providing a basis for comparing the consistency of the approach across countries. Once these prices were established, a matrix of the expected durability classes given development pattern was established for all structural types. For Tanzania, the permanent material replacement cost was $339 US, the semi-permanent is 141, and the temporary material replacement cost is valued at 61 US. Here we have the estimated replacement cost values for Dar es Salaam. The building height values for all development patterns were directly obtained from the field survey data collected by HOT OSM. This established the building height by structure type per development pattern. Rural areas are assumed to be 100% low-rise. The HOT OSM survey was reviewed and validated by an in-house engineer using the images provided of the individual buildings. Building area values were directly obtained from the field survey data collected and the aggregated building area raster. The total building area was calculated using a combination of the humanitarian OpenStreetMap team survey data and the 3 arcsecond aggregated OSM building area raster datasets created by ImageCat. For the rural development pattern, the average building footprint area from the 3 arcsecond aggregated OSM raster was used to determine the average total building area, assuming all rural developments are single-story. For all other delineated development patterns, the HOT OSM in situ building survey was used to establish the total building area by structure type per development pattern types using the surveyed building footprints and height value. And finally, there was an adjustment of building size to reflect the urban development pattern. There is a great deal of information that goes into creating a building exposure. The aim of these flowcharts is to 1. Assist future researchers in updating and refining the exposure database as a whole or fine-tuning individual sections with improved data. 2. Assist in organizing the metadata collection. And 3. Work through the logic of the processing steps. That concludes the flowchart demonstration. We hope that these flowcharts assist you and the future teams in conducting, updating, and refining a Level 3 building exposure. Thank you, and have a good day.